This is acids, bases, and salts. Acids and bases are chemical substances that release certain ions when dissolved in water. There are two categories of acids: binary acids, those that do not contain oxygen, and oxyacids, those that contain oxygen in the formula. We didn't do naming of acids, and I think it's good to do it here. Okay. So when we did ionic and covalent naming, I didn't want to have so many things together, so I want to do it in this section. So when we name acids without oxygen, we just use hydro plus the root of anion plus IC. That's it. So if you have HF, hydro, fluor, I can't even, fluorine plus IC. So that becomes hydrofluoric acid. This is more like a formula. You just have to bring these together and then you pronounce them together. You see, hydro, brom, okay, that's the root of anion, okay? Remains the bromide, then you have brom, then plus IC, so hydrobromic acid. The same with hydroiodic acid, which is very easy. Then, in naming, if the acid contains oxygen in the formula, which is oxalic acid, the ion present in the formula is going to be a polyatomic ion. You don't have to memorize the polyatomic ions, but some people do. I think after you use it for a while, you get used to it. So what you do, identify the polyatomic ion in the formula, because the name is going to be based on that polyatomic ion's name. So you can get the list of polyatomic ions. So if the polyatomic ion's name ends in ATE, then change the ending of that ion to IC and add the word acid. That's it. So for example, determine the name of anion here. The anion here is sulfate. It ends in ATE. So because it ends in ATE, we change that AT to IC. So it will be sulfuric acid. Sulfuric acid. Then another example, if the polyatomic ion ends in ITE, change the ending to OUS and add the word acid. So sulfite. ITE to IC. So the name is sulfurous acid. This is very easy. Then more examples, you can have phosphoric acid, nitric acid. Then properties of acids. Acids are electrolytes. They conduct electricity. Turn blue, litmus paper red. You have sour taste. React with metals to form hydrogen gas. Examples are vinegar, soft drinks, apples, citrus fruits. These are all examples of acids, things that contain acid. Then properties of bases. Bases are electrolytes, also turn red litmus paper blue. Bitter taste, slippery like soap. Examples are ammonia, lye, antacid, soap, baking soda. Okay. What is acid? There are different definitions of acid. Actually, there are three models. The two models are most common. There are three models in on the 3 ways of defining acid, 3 different models. There's Arrhenius model. According to Arrhenius, in aqueous solution, acids form hydrogen ions. Bases form hydroxide ions in aqueous solution. Something like this. So that means Arrhenius is saying that acid has to be a hydrogen-containing compound, because being a hydrogen-containing compound, in solution, they give off hydrogen ion. And then base has to be hydroxide-containing compound. In solution, they give off hydroxide ion, which is this. These are all examples of Arrhenius acids. Each of these will give hydrogen ion in solution. So another model is Bronsted-Lowry model. And it says acids are substances that donate 1 or more protons to another substance in a solution. A base is any substance that can be a proton acceptor. Proton acceptor. Note, hydrogen ion is a proton. So look here, if you look at this equation, here, hydrogen donates the proton and water accepts the proton. So hydrogen, hydrochloric acid is this is the acid, and water is the base here. So now we have hydronium ion and chloride ion. Okay. So let's look at conjugate acid and base. So conjugate base is what remains after the acid donates a proton. Conjugate acid is what is formed when the base accepts a proton. So looking here, this is base. Why is it base? Here, water acts as the base, accepts the proton. And when it accepts the proton, what is formed is conjugate acid. We call it conjugate acid. When the base is accept the proton, what is formed is conjugate acid. And then when it donates, acid donates, what is remaining is called conjugate base. Okay. So this is another way of looking at it. I think this shows exactly that this Bronsted is more, it's not as narrow as Arrhenius. Why? Because here we have water, we have the water donates the proton, so water acts as an acid. Okay, donates the proton, this is what is remaining after it donates the proton. And then here, the proton is accepted by NH3 and becomes conjugate acid, so which is this. So here, ammonia is a base and water is an acid. Remember, water is amphoteric. It can act as a base and it can act as an acid. It's amphoteric. Okay. So that means, according to Bronsted-Lowry, ammonia is a base. Okay. And water can be an acid. Why is it a base? Because it's the proton acceptor here. It accepts proton. That's why, because it accepts proton, it becomes HH4 plus. Water donates the proton, which is accepted by the C. Water donates, remove, and that proton is accepted by NH3. So there's Lewis model of acids and bases. This is not as common as the other two, but it's good to know that there's a third model. So according to the Lewis model of acids and bases, an acid is any substance that accepts an electron pair. Acids are electron pair acceptors, bases are electron pair donors. So if that is the case, base donates the electron pair, look at it here, which is accepted by the acid because acid are electron pair acceptors. I just want to make mention of this. Okay. Then let's look at strong and weak acids. What's the difference, and bases? What's the difference between them? Strong and weak acids. So strong acid, you see strong acid, you have a lot of hydronium ion, which we can see here. Hydronium ion, a lot of it formed. Okay. There's 100% ionization here. Then let's look at strong base. Or rather, let's look at weak acid. Weak acid. Do you see weak acid? There is so reversible reaction, meaning it's not 100% ionized. Look at it. You started off with this. We still have is partially ionized. Not 100% ionized, it's partially ionized. That's weak acid. Okay. So you see that? You don't have a lot of hydronium ion. It's partially ionized. That's why it's a weak acid. And then strong base. Strong base. This is dissociation. It breaks apart. Weak base. Okay. Weak base partially ionized. Okay. Now, so strong acids transfer 100% of its protons to water in an aqueous solution. So it's about 100% ionized. So you see this thing lies far to the right. Then examples of strong acids are this. Strong bases completely dissociate into its ions in water. Example of strong bases are this. Then weak acids partially ionizes an aqueous solution of water. Example of weak acids. The most common one is weak base is ammonia. Weak base. Then we look at neutralization reaction. This is a very important reaction used a lot in everyday life. Neutralization means that an acid and a base have reacted to form a salt. Form a salt. After when you started this acid, this is base, but the salt is neutral. Okay. Any ionic compound that forms from the neutralization reaction between an acid and a base, that's what salt is. Salt is formed from neutralization reaction. So you have acid and base, gives salt and water. Okay, this is neutral. Okay. In labs, if you remember in lab, when you do lab, if you do something that is really acidic or basic, you neutralize it before you dump it in the sink. Okay, neutralization reaction. We use neutralization reaction a lot. You use a lot in chemistry lab, can use a technique called titration to determine the exact concentration of unknown solution. Okay. So what is titration? This is the analytic method in which a standard solution is used to determine the concentration of an unknown solution. Use it to determine the concentration of unknown solution. In real life, Used in hospitals to determine the concentration of chemicals in the blood and urine. Used to figure out the fat content and water content or the concentration of vitamin in food. It's used during the very precise manufacturing process needed to produce medications of the proper dosage. Very useful technique, very, very useful. So with everything done, go through this and identify as acid, base, and salt. Justify your answer. When I say justify your answer, there are so many ways you can justify your answer. You can say why. You can use Arrhenius definition or model to describe. You can use Bronsted-Lowry to describe it, or everything covered in this chapter. There are a lot of information here you can use to justify why it's acid, base, or salt. So you have to understand the concept in this video very well for you to write a very good justification. I hope this makes sense. Thank you for watching.